I'm president of the board, John Simpson, and commissioner for the at-large position. Our first presenter tonight is Dr. Peter Valberg. He is a principal in health risk assessment at Radiant, an environmental consulting firm that evaluates human health risks from various environmental sources. Dr. Valberg specializes in quantitative analyses of exposure, dose response, and health risk for both substances and for ionizing and non-ionizing radiation. His educational background includes both an MA and Ph.D. degree in physics from Harvard University and an MS degree in human physiology from Harvard University School of Public Health. He served for 25 years as a faculty member at Harvard in the Department of Environmental Health, teaching physiology, toxicology, and electromagnetism. Among the research grants that he directed was one funded by the National Cancer Institute on magnetic field effects in cells. He also served on the Harvard Advisory Committee on EMF and Human Health, and the Harvard University Peer Review Board on Cellular Telephone Technology and Human Health. Dr. Valberg has also served on advisory panels for the National Institutes of Health, the Health Effects Institute, Department of Energy, National Academy of Sciences, the Environmental Protection Agency, and the World Health Organization. Of particular note, he worked with the World Health Organization on the health effects of cellular telephone technology, a study that was published in the journal Environmental Health Perspectives. Dr. Valberg is based out of Cambridge, Massachusetts, and we welcome him tonight via webinar to our meeting.
Yes, thank you very much. I appreciate that introduction, and I guess I will assume that you can hear me okay, because there's no way that I can get your normal feedback from the audience that I would get if I were there in person, and I apologize for not being there in person. But yes, my background is basically public health and human physiology, and I've studied this area of electromagnetic fields and radio frequency fields for a number of years, and I was asked to present some tutorial items to the U.S. boards here about radio frequency waves and how that might relate to potential health effects from smart meters. Now, I'm going to talk about a few topics, and I'll take maybe I can stop in between them if necessary, but otherwise, for the sake of time, I will press on. The basic question that confronts us here is there a particular RF intensity that can lead to adverse health effects? And in order to set the stage for thinking about answers to that question, I'm going to talk a little bit about questions like what are electric and magnetic fields and what do they do? What are radio frequency electromagnetic waves? How do different electromagnetic waves compare? What determines the dose when you're talking about these kinds of waves? What determines biological response? And then certainly touch on what kind of RF levels are associated with smart meter operation. And then that will be essentially the first part of my presentation. Then I'll go on to discuss what kinds of investigation scientists use when they try to gather evidence. What is the evidence for health effects of RF, and what kind of scientific expertise is applied when you design these experiments and interpret the results. Then the last part of my presentation will be a little bit of summary on how does this scientific data get pulled together. What are the public health review group conclusions in this area, and how do they examine both the strength and the weight of the evidence? All right, well, let's begin a little bit with just the electric and magnetic field. They may be kind of mysterious, but since this is a board that deals with power lines and electric fields, it's probably, maybe this is repetition, that electromagnetic waves are really just electric and magnetic fields that oscillate in time. And then you could step back and say, well, what are electric fields and magnetic fields? Well, they're really defined operationally, if you will. Electric fields really mean seen that there's something there that exerts a force on electric charges. Magnetic fields conversely exert a force on moving electric charges. And that's really all there is. I mean, that is the basic definition of electric and magnetic fields, which are, if you will, concepts that scientists have created for interactions between electric charges. Electric charges create electromagnetic waves, and electromagnetic waves in turn act on electric charges. And so that's essentially all there is to the nature of electromagnetic waves. Now, they've been around for a long time, and I just wanted to very quickly explain that scientists have studied electromagnetic waves for more than 150 years. It was back in the 1860s that the physicist James Clerk Maxwell predicted how electromagnetic waves are created. He predicted how they interact with matter, and he showed that these electromagnetic waves would travel at the speed of light. And he did this already on the basis of what was known about electricity and magnetism. It wasn't until the 1880s that Heinrich Hertz, another physicist, experimentally demonstrated the existence of such electromagnetic waves and that they in fact were real entities. And almost very quickly after that, Marconi and others jumped on the bandwagon and started using these. And in fact, Marconi was awarded the Nobel Prize in Physics for inventing radio. He used these electromagnetic waves to transmit information without wires, and so that became known as wireless communication. And since, you might argue that since 1909, we've all utilized wireless communication in a whole variety of forms. And in fact, all the way from 1909, or let's say even all the way from 1860, when Maxwell produced his theory, to 2013, Maxwell's equations have held up. I mean, there's been no unexplained electromagnetic phenomena, and there have been no exceptions found to Maxwell's equations. So it's a technology that we've used a lot, that engineers have created a lot of new devices with. And aside from the addition of quantum mechanics to electromagnetic phenomena, the understanding that we have for the past 150 years of how this interacts with matter is still good. And as I say, no exceptions have been found. Now, the electromagnetic waves come in a variety of frequencies, and this diagram just shows that different types of electromagnetic waves make up what's called the electromagnetic spectrum. And this electromagnetic spectrum is just characterized by electric and magnetic fields that oscillate. They oscillate in time in terms of cycles per second, and the unit for that is hertz. And they range from low frequencies to high frequencies, the very lowest ones being the ones that we're accustomed to for power lines down here at the bottom. And then you go up through radio, television, cell phones here at around 1,000 megahertz, microwave ovens. And as you go up in oscillation frequency, you get to infrared light, and then to visible light, then ultraviolet light, and then on up into X-rays and gamma rays. And there is an important boundary that occurs right around ultraviolet light, where the electromagnetic spectrum is divided into so-called ionizing radiation above, or frequencies above that ultraviolet range. And then in this lower range, it's non-ionizing radiation. And there'll be some important differences there that I'll point out to in a minute. But there's a whole spectrum. That's all electromagnetic waves. And they just differ in frequency, and they go over a vast range of frequencies. Now, one of the important things is that there is this difference between ionizing radiation and non-ionizing radiation, and that difference is determined by the frequency. Now, ionizing radiation can alter molecular structure. Non-ionizing radiation cannot, because the distinguishing characteristic is the energy of the so-called photons. The thing that quantum theory added to Maxwell's theory was that the energy in the electromagnetic spectrum comes in little packets, little energy packets called photons, and the size of those packets increases in energy as you go up in frequency and as you go up in the electromagnetic spectrum. So the ionizing radiation, for example, X-rays, have a very high frequency. We can say here 100,000 trillion cycles per second, which you can express as 100,000 terahertz if you're into units like that. On the other hand, in the cell phone region and with smart meter radio waves that give a much lower frequency of 1,000 million cycles per second. And that is typically abbreviated as about 1,000 megahertz. And so just to make sure that people are not confusing radiation, the term radiation, if it's applied in this radio range with ionizing radiation, it's important to recognize that the smart meter radio frequency is more than 100 million-fold lower in frequency than ionizing radiation. So it's far out of the ionizing range. It's below visible light and so on. But that distinction is quite important when you start thinking about how the radiation interacts with matter, and particularly how it interacts with biology. You can kind of show that on this diagram, which I just put together to show the trend from high to low, because for electromagnetic waves, the frequency actually determines what kind of biological effects can occur. And then I'll say a little bit more about that. And here at the very top, you have high oscillation frequency, gamma rays, cosmic rays, nuclear radiation. Below that, medical X-rays, far ultraviolet light, those are still ionizing. And then as you go down in frequency, you get to visible light, which is electromagnetic waves that we all see with, and that's in the non-ionizing region. And below that, in frequency, is infrared light, and below that, in frequency, are the microwave and radio frequency waves that are associated with smart meters, and below that, we even have the very slowly varying electromagnetic fields from power lines. So you have this hierarchy of energy that's contained in the electromagnetic fields. Now, the energy, and I apologize, this is probably one of the more numerical slides I have, but it is important to emphasize that the energy in ionizing radiation is quite high when you talk about it in terms of the energy units called electron volts. So soft X-rays have an energy, those photons have an energy of 1,000 electron volts. And they're strong so that when they shine on matter or biological tissue, they can actually disrupt chemical bonds. They can break DNA, they can break proteins, they can break enzymes, and that's because they have a lot of energy per photon. Ultraviolet B light is about 5 electron volts. They can still ionize molecules and break them apart. Visible light, its photon energy is about 2 electron volts, that's yellow. And that can bend molecules, but it can't really break them apart. In fact, bending molecules is the primary event when we see something. Vision is caused by bending of molecules in the eye. Below visible light, there's infrared, and that goes down lower, but that can vibrate molecules, but the energy levels you notice here are dropping off dramatically. Below that, you have millimeter radar, which can vibrate molecules. And then when you get to smart meter RF, you're really down to the region where only the electric and magnetic fields act on ions and charges. That is to say, they can weakly push on ions, but they can no longer cause molecular changes or disruption of chemical bonds. And so this spectrum of energy is important to recognize when you're talking about biological effects. The next thing, in addition to the energy per photon, you have to ask yourself, what is the intensity? What is the amount of electromagnetic wave which is being either put out or absorbed by your body? First of all, let's look at radio wave emission power. And again, it's just important to have a general scale on how the society uses radio wave emission power. And here again, I've arranged them from high to low. The biggest sources of radio wave emission power, of course, are commercial AM and FM radio transmitting towers, analog and digital television transmitting towers. Those put out a lot of RF energy. Below that, and actually comparable to that, are military radar, aviation radar, marine radar, weather radar. Those are all, again, electromagnetic waves that are used at fairly high energy. Then there's a plethora of local sources, medical emergency, fire, police, dispatch services that use radio waves. Inside our homes, we have microwave ovens, cellular and cordless telephones. Outside the home, there may be a cellular phone base station, but those are lower energy again in terms of their emission rates. And then we have many consumer items, walkie-talkies, AV monitors, wireless routers, cordless phones, alarms, and so forth. Smart meters are down in this fairly low region because the amount of energy that they can actually create in the radio wave spectrum is fairly limited. And so I won't spend much time on this. This essentially just repeats what I just said, that RF energy comes into our homes all the time because we know we can turn on televisions and radios and we can tune in stations. And that very fact indicates that radio frequency energy is coming into our home. And likewise, the energy from lots of emergency services are coming into our home. We use lots of devices these days that are wireless, that also use radio waves. And in fact, radio waves can also be created by ordinary appliances by virtue of their electronics, or if they have motors with brushes, and those sparks create radio frequency interference. So there are many sources of radio frequency waves, and this is just by way of explaining that these radio frequency waves are something that we've had in our environment for quite some time, and we've utilized them a great deal for communications purposes and actually other medical purposes as well. There are many medical procedures that use microwaves specifically to heat tissue, to do surgery on tissue, and so on. If you wanted some actual numbers, I mean, typical AM, FM radio transmitting antennas in the range of 50 to 100,000 watts. If you go up to UHF TV, those powers are usually in the range of a megawatt, 1 million watts of radiated power. That's actually much larger if you compare it, for example, to a typical cell base station. Those are in the hundreds of watts. I mean, I would say of the order of 200 watts. Military radar is quite powerful. It's about 500,000 watts. Here in Massachusetts, we have an installation called PAVE, which is looking for missiles coming over the horizon, et cetera, and that's 600,000 watts. And then to step into a slightly different frequency range, I do want to point out that there's also a lot of radiation in the infrared region, which is above the radio wave region. You can turn on an infrared heater, and those heaters are typically 5,000 watts. So when you bask in the glow of an infrared heater, that's about 5,000 watts, again lower, but quite high. And then finally, it's important to recognize that even our own bodies are electromagnetic wave radiators in the infrared region, and that is at about 100 watts. That is to say, infrared radiation from our body can be detected by night vision goggles and by night vision cameras, and that's because we're all glowing in the dark. And even if there were no visible light in a room, everybody would be lighted up by this infrared radiation coming from your body. So that's actually quite high. It's in fact quite a bit higher than the energy coming from a flashlight, which is both visible and infrared. That's of the order of 2 to 4 watts. And then smart meters, which are not infrared, but they're radio wave, but the amount of energy coming from them is quite small compared to the amount of energy that we're all putting into the electromagnetic spectrum from infrared waves. So one of the things that, again, is helpful when you're thinking about radio waves is to think about how our body is, what kind of environment is our body living in? What are the thermodynamic facts about a body that's living at 37 degrees centigrade? It essentially is operating in a bath of infrared electromagnetic waves. And as I said, our bodies radiate electromagnetic waves, and they can be seen with night vision. It's at a rate of about 100 watts. If you run fast or pedal your bicycle fast, it goes up. The amount of energy that you're putting out goes up. And so what that means is that our body's organs, cells, molecules all function in a bath, a 100-watt bath of infrared photons. Those photons have more energy than radio frequency photons. And so if you were to compare the electromagnetic interactions of our bodies, if you will, to the 1 to 2 watts of radio wave frequencies that you are concerned about in the case of smart meters, then you see, well, number one, radio waves are lower photon energies, and that amount of energy is actually small compared to the total amount of energy that you're radiating as a human body. Then finally, the molecules in your body, including proteins and DNA and smaller molecules and so forth, are undergoing motion because of this thermal energy. And they're colliding with each other. There's about 1,000 billion collisions each second. And those collisions, it cause strong electric fields locally because that's the way, that's the nature of collisions between small objects. They're basically electrical collisions. And so when you're thinking about how you're going to get this energy to do something in the biological environment, you have to remember that you're trying to do something in an environment that's warm at 37 degrees and already has a lot of electrical energy going on in it. Okay, now the next thing to look at is not so much the emission like you might have from an antenna, but what is the amount of energy that's falling on the surface of your body? And again, I'm looking at a cross-section of frequencies. I'm comparing sunlight to radio waves, but it's important to remember that sunlight is electromagnetic waves, and the amount of electromagnetic energy in our environment is vastly dominated by sunlight. The amount of energy that sunlight generates is about 1 kilowatt per square meter at the Earth's surface at noon on a summer's day. Just to jump from that immediately to the FCC public safety standard for smart meters, which are about 910 megahertz in frequency, that safety standard is 610 microwatts per square centimeter. So it's a very small amount of energy. And in fact, you may have already seen some of this in the literature and in other sources. The RF levels near smart meters are quite a bit below the standard. This standard is important for bigger sources, and in fact, those bigger sources have to meet that standard. But smart meters don't have a very hard time meeting that standard because even if you're as close as about 3 feet, you're in the order of about 4 microwatts per square centimeter. So the amount of electromagnetic intensity that you're dealing with here, and this is when they're on, the amount of electromagnetic intensity is fairly low. Now, you can go to the literature, and there have been studies that are published about smart meters, and here's one from a journal called Radiation Protection Dosimetry. And that's a long article, has many things in it, and I'm just going to focus on a couple of things. Before I look at this graph, I have to point out to you that very often when you look at these graphs, the intensity of the field is often given as a percentage of MPE. And what that means is they're giving it as a percentage of the maximum permissible exposure. And so sometimes that can be a little strange because we were just now talking about microwatts of energy per square centimeter. And so the way you do that conversion is just to remember that the guidance for general public exposure at smart meter frequencies, which are around 900 megahertz, the maximum permissible exposure is 600 microwatts per square centimeter. And so if you take 0.2% of that, if you multiply that together, 0.2% is 1.2 microwatts per square centimeter. So up here on this axis, here's 0.1%. So 0.2% would probably be right about there. So I put a little arrow there, and that arrow says 1.2 microwatts per square centimeter. Now, what's characteristic of all radio wave sources, and certainly smart meters in particular, because they have such small antennas, is that the radio frequency level drops off very dramatically with distance. This 1.2 microwatts per square centimeter is occurring right here at a distance of about 1 meter. This bottom axis is in meters. And so we're having 1.2 microwatts per square centimeter at 1 meter. But you notice these things fall off in orders of magnitude. So if you went down here, you would be 100-fold lower. And that would be 0.012 microwatts per square centimeter. So the energy levels are low, and they do in fact decay quite rapidly with distance as you move away from the antenna that's inside the smart meter. And so in that article, they basically looked at smart meters both turned on and then under the normal operation where they don't necessarily operate all the time, but they operate in bursts where between 6 times a day for periods of the order of milliseconds, the smart meters transmit data on energy consumption as gauged by the utility meter, and then, when the maximum transmitting power is 1.5 watts. The transmitters that are inside these meters are very limited. They can't put out much power at all because they're just not designed to. Anyway, the authors concluded that the RF transmitters and wireless equipped smart meters operate at similar power levels and similar frequency ranges as many other digital communications devices in common use, and their exposure levels are very far below U.S. and international RF allowable public exposure limits. Now, in addition to the public, the peer-reviewed literature, there are also lots of reports on smart meters, and one of the most recent ones was in Vermont. The Vermont Department of Public Service in January of this year published a report, you can get it on the internet, that reported RF levels for smart meters that were actually in operation in field conditions. The title of the report was an evaluation of radio frequency fields produced by smart meters deployed in Vermont. And just for the sake of concreteness, the results were shown in a few places in the report, and I'm going to focus on a graph on page 37. And again, the RF fields were expressed as a percent of the MDE, the maximum permissible exposure for general public. And so I just repeat what I said before, the guideline at 900 megahertz, it's 600 microwatts per square centimeter, to 0.2% is 1.2 microwatts per square centimeter. So I took this particular figure because it was interesting. It had to do with actually measuring the field at a site that had more than one smart meter. The blue line corresponds to a metering location that had 5 meters operating simultaneously, and the red line, an even larger one, that had 36 utility smart meters operating simultaneously. And here the bottom axis is in feet. Here is the peak field, again expressed as a percentage of the maximum permissible exposure. And again, what you see is the same pattern, a little bit of noise because these are very weak signals and they're hard to detect. And so the field levels drop off with distance in both cases. And if we put our little 1.2 microwatt per square centimeter arrow here at 0.2% MPE, we see that within a distance of about 3 to 4 to 5 feet, the field levels have dropped off to this low level, which is, as I say, 0.2% of the standard. The standard is applicable both in the United States and internationally and so on. Okay, at this point, I'm going to change gears and talk a little bit about health effects research. And if I'm going too fast or too slow, you can feel free to interrupt me or ask questions, but I'm going to go on and talk a little bit about health effects research. Hearing nothing, I will go on. And then the first thing to think about in terms of the research is what kind of knowledge areas are necessary when you're trying to do reliable scientific research on RF health effects. Well, it is a little bit of a peculiar area because you need to understand the physics of RF and to know what all the sources are, whether there can be interference between different kinds of sources. You'll want to develop a radio frequency dose response. And here, it's very important to know what the homogeneity of your RF exposure is. You don't want to have hot spots. If you had, for example, set up your system in a way that you had a very inhomogeneous RF exposure, that would not be good. It would not give you reliable results. You need to know the response of certain markers. If you're going to use genetic markers or molecular or cell biology markers to determine what the bio effects are going to be, so you have to know how those behave and what other things might change them. If you're using animals, then you need to know how the animal behavior might be affected by the exposure system in ways other than the RF exposure. What's the physiology of the animals? Are there noise and temperature responses that you need to be concerned about? If you're looking at human populations and you're applying epidemiology, then you need to have a good knowledge of the necessary statistics. And in fact, there's also a set of criteria that's often referred to as Hill's criteria that determine whether whether or not the epidemiological study, can be considered reliable. In epidemiology, it's very important to consider the possible sources of bias, because you might think that you're studying, for example, RF exposure, but because our lives are so complicated, there are many other things that vary from person to person, and that can give rise to bias. And so those are the kinds of things you have to worry about. Now, the scientific investigations come in three avenues of evidence, and I think it's important to recognize that these avenues of evidence are separate, and yet they're complementary. They should support each other. First of all, you have population studies, and population studies can be either of people, there's like broad-based general public cell phone use. I mean, that's one RF exposure that many people are exposed to, and so you can get large numbers of people. Or you might look at high exposure levels in workers. There are some occupations that have RF exposures. You can track those, see if there's any differences in patterns of disease. And so these are population studies that use epidemiology, and they're powerful in the sense that they apply to people, but their weak spot is that they're statistical. They're observational studies, and they're not really experimental studies. They're more statistical associations. In toxicology, the gold standard is often laboratory studies on multiple species of animals. And so there are, in fact, studies where you can expose animals to RF. You try different species. You can do short-term acute exposures, chronic, lifetime studies, and so on. And again, that's a very important line of evidence. And it's, as I say, the gold standard of toxicology. Its only drawback is that you aren't getting information on mammalian species, but they're other than humans. So then you have to think about the extrapolation of those results to human beings. And then finally, you have in vitro exposure systems that look at tissues and cells and molecules. And this particular line of investigation looks for biophysical or mode of action for the radio frequencies. And so these things can be thought of as the three legs of a three-legged stool. And so the strength of evidence about knowing how something behaves in terms of health effects is like the stability on a three-legged stool. You can look at all of the lines of evidence and see whether they are coherent. Maybe they're not coherent. Maybe they're discordant. But in the situation where you're going to develop standards, you really need lines of evidence from all three of them, because they all contribute to knowing what the standard should be for, what levels are involved, and what kind of adverse health effects you're trying to protect against. Now, when you look at the published literature, literature comes in all of these different flavors, ranging from epidemiology to animal studies to mechanism. You have to be a little careful in trying to get a broad and a broad picture that's sufficiently valid. You want to avoid what's called the microcosm, focusing on a single explanatory factor behind multiple risk associations. Because generally speaking, any kind of adverse health effect has multiple causes. There's also the pitfall of selective attention to positive studies with a lack of focus on null results and negative findings. In fact, there is a name to the fact that often negative studies don't even get published, and that's called publication bias, because investigators feel that editors are not going to be all that excited about a study that didn't find anything. Each individual study has to be looked at for its strengths and weaknesses as to possible internal errors. The most predominant internal error is unblinded. Blinding means that the investigators and laboratory workers do not know which are the exposed animals, cells, populations, and so forth, versus which are the exposed ones. If it's not blinded, there's always the possibility of some kind of subjective bias, which could confound the results. There could be multiple comparison issues. There could be a lack of controls. There could be a lack of dose response. There could be exposure error. So there's a possibility of systematic internal errors that have to be watched out for. Then you have to look broader than the individual study. You have to look at relevant data as to how this dose that is studied in that particular investigation compares to others. How does the mechanism compare? Were there co-exposures that need to be concerned? What was the time duration? Were the statistics okay? Were they significant, and so forth? And then perhaps most importantly, studies is the issue of replication. That it's possible to see a lot of studies out there that report an effect, and it's interesting, and it looks like it could be intriguing and so forth, but then that you find that there's a lack of repeating that same study in other laboratories to see whether it's really real, or perhaps it was a red herring kind of result. And so when it comes to reviewing this and essentially getting together the public health groups that review them, you have to also, therefore, look at the same type of expertise that we looked at earlier. You need the physics and RF engineering expertise to see whether the dosimetry was right and whether the exposure was correct. You know, you have to have laboratory animal and cell culture expertise to know whether the temperature was controlled, were the cells happy, were there other variables, were there possible infections in the animal, possible infections in the cell. And you need to have expertise in outcome interpretation. How significant are the genetic changes? Maybe you're looking at so many genes that you're always going to find some genes that change, and you need to know whether the number that change are in fact statistically significant. You need to know how you look at organ pathology, how the molecular biology markers compare, and so on. And then you can look at the statistics. I mean, what are the chances that it was a chance result? And typically, chances usually ruled out only to the 5% level. I mean, 95% confidence that random error has been ruled out is the standard thing. If you think about it a little bit, it's a little daunting because it essentially means that an awful lot of results could be false, because by definition, 5% of the remaining results still could have arisen by chance. So you need to be careful about that and take that into consideration. In terms of those three legs of evidence, none of them really support the fact that weak, here I'm emphasizing the idea weak, RF exposures are hazardous to health. Now, high enough RF exposures do deliver enough energy, and the RF standards, which are thought to be health protective, are designed to prevent exposure of individuals to higher RF levels. In terms of the three legs, the epidemiology of RF exposed worker populations is generally not supportive of health effects when the exposures are below RF standards. There's been a lot of epidemiology of cell phone users. The so-called interphone study is one of those. It doesn't really support an RF adverse health impact. Now, there are many bioeffects that are reported in cells and animals exposed to RF. But there's two problems. One is this lack of reproducibility. I mean, they're not very consistently replicated in other laboratories. And then secondly, some of them are of uncertain relevance as to what outcome they're actually predicting. I mean, is that outcome a viral effect? Is it something that's going to lead to an adverse health effect or not? And then perhaps one of the really key ingredients is that despite a lot of focused attention by some side of the issue, we've not found a biophysical mechanism by which weak RF could disrupt cells and biological molecules like DNA. You know, this gets back to some of the principles that I was talking about earlier, having to do with what is it that RF could really do. So,
Dr. Valberg?
Yes.
This is Janine. I'm checking the time, and I'd like it if you could wrap up pretty quickly. So we have time for questions.
Sure. Yeah. No, I will wrap up very shortly.
Okay.
I'll leave out one section, and that will help a lot.
Okay. Thank you.
And so, in terms of mechanism, you could say, well, yeah, you have ions, molecules, and so forth. Maybe these RF waves can push and pull on them in a way to change biological function. But the issue is you have to look at the size of those forces. That the weak forces cannot really be detected in the noise of existing electrical activity. The RF forces average to zero. We haven't found a mechanistic basis, and the molecules, as they collide with each other. I won't discuss this chain of events, but in order to have RF exposure be the cause of an adverse health effect, all links in the causal chain need to be completed. And then ultimately, these individual studies need to be synthesized by these expert panel reviews into synthesis. So, to summarize, no coherent pattern of disease has emerged. The animal studies have not uncovered the causal chain. The mechanism of action has not been identified. And what aspect of it is, what aspect of low-level EMF, whether it's frequency, amplitude, modulation, is really unknown. And, you know, we've used RF in densely populated regions for more than 100 years, and we've seen no indication that such RF exposure increases human disease. Research has been going on for quite a while. It was probably in the 1950s that it really picked up, and it continues to be addressed. And so I don't think there's a lot of reason to think we've missed gigantic things. And there are a lot of independent consensus groups that are composed of research engineering, medical, and public health scientists that have reviewed the data and examined all the aspects of RF safety. And these groups have developed guidelines for safe level of RF exposure that take into account all the scientific literature, both the so-called thermal effects and the non-thermal effects. Okay, now IARC, the International Agency on Research in Cancer, in 2011, they were looking at a lot of cell phone literature, laboratory data, and so forth. And they, in fact, gave cell phone use a 2B rating. And I just wanted to spend a couple minutes explaining what that was. The International Agency for Research on Cancer periodically reviews the science on chemicals and things people are exposed to and categories. And there are these categories right here. Group 1 is called known human carcinogens, and of all the things they've looked at, they've put 111 items in there. 2A is probable human carcinogen, they put 66 in there. 2B is possible, they put 285 in there. And then there's a whole bunch they reviewed that they couldn't decide whether they were carcinogens or not, and so they put them in this group 3 category. And so IARC's ranking of heavy cell phone use as Group 2B was not really directed at smart meters. It was really directed at the cell phone literature. So that's point number 1 to remember. But you notice this Group 2B category is quite large. There's lots of things in there, and it is a category that's called possible. And it includes many everyday items. I mean, carbon black, which is a constituent of car tires, that's in that category. Coffee is in that category. Doing carpentry is in that category. Talc, nickels, like the nickels that we have in our money, iron pills, pickled vegetables, mothballs, some teas. So there's a lot of materials in there that they couldn't really say, well, we'll eliminate them, but we'll put them in the possible category. But just for the sake of comparison, it might be interesting to note that IARC, in fact, classifies some ordinary things in these higher categories as well. And the one that maybe sticks out is that IARC classified both sunlight and sand. Those are known as IARC Group 1 carcinogens. Sunlight because it causes skin cancer, sand because it contains silica. And so they're Group 1, they're known human carcinogens. And so yet, you know, we don't generally keep our children on sunny beaches, which have both sunlight and sand, because of these IARC classifications. So, you know, these classifications also do not take into account dose. They're just the IARC looking at these substances and asking themselves, you know, might they cause some increase in cancer risk? And they go through this process, and as I say, they put a whole ton of things into these categories, and that's where they put both cell phones and they put power line fields also in that category. In terms of health organizations, it's important to remember that they do review non-thermal effects, but they basically say they can't really demonstrate that they lead to disease. The World Health Organization, after the IARC classification, stated to date no adverse health effects have been established as being caused by mobile phone use. Britain's advisory group on non-ionizing radiation concluded in 2012, although there's a substantial amount of research that has been conducted in this area, there's no convincing evidence that RF exposure below guideline levels causes health effects in adults or children. So I guess one of my messages tonight is that the recommended approach is really try to rely as much as possible on legitimate public health agencies, because none of the Blue Ribbon scientific review groups have determined that RF levels from smart meters are harmful to health. And so I think that those are kind of safe harbors, if you will, to look at, and they have a lot of people that are constantly reviewing the scientific literature, and they produce voluminous reports that you can look at and read and see what all the nuances are. And then I just did want to mention, because I noticed that your own Oregon Health Authority in the form of Dr. Katrina Hedberg had in fact done some review and came to the conclusion that the Oregon Health Authority Center for Health Protection reviewed recent peer-reviewed scientific literature on the subject of health effects from radio frequency radiation. And what she stated was, based on our review of these reports, evidence from the scientific literature, and consultation with radiation experts, we conclude at this time that the implementation of smart meters will not adversely impact public health. And, this tells you an important message. Science can never prove a negative. You're never going to be able to say, okay, here's the experiment that shows that this particular health effect is impossible. Science can only move forward by summarizing the weight of the evidence and the strength of the evidence and seeing, is it really strong enough to say that we believe this is an important public health issue. The last section was just to look at some of these issues about, things that you might hear about RF fields, and please stop me if this is all repetition and so forth. The internet gives us all sorts of views. What is it, when you look at these claims of adverse health effects, what is it you need to look for? Well, you need to examine the strength of the evidence. What's the accuracy? You need to examine the consistency, the weight of the evidence. And then another thing that is probably important is examine how coherent it is, meaning, are there multiple studies that show the same thing, which means, do public health agencies act upon the claims or articles cited? And for example, one thing that you can find is something like this, which shows the mortality of U.S. Navy Korean War veterans, stratified in this chart. This chart shows stratification by in-service levels and occupational radar exposure. It's from Robinette in 1980. And what it seems to show is that total deaths, disease, cancer, lymphoreticular cancer, as you go from low exposure to intermediate exposure to high exposure, it goes up. So that looks a little bit alarming. But, what you need to do is to go back to Robinette in 1980 and see what, did Robinette in 1980 find that radar exposure increased disease? If you look at the original article, this is just a little cutout of the original article, Robinette and colleagues, Silverman, Jablon, 1980. The abstract says, doesn't say that. In a study of 40,000 veterans, no adverse effects were detected in those indices that could be attributed to potential microwave radiation, 1950 to 54. Conclusion, differential health risks attributable to occupational exposure to radar in the Navy over 20 years are not apparent with respect to long-term mortality patterns, hospitalized years, illness around the period of exposure, and so on. If you actually look at tables, I'm not going to belabor this, if you look at tables of all diseases, malignant neoplasms, this is from Robinette, page 45. The differences between low exposure and high exposure are basically not statistically significant, and in fact, if they're close to unity, that means that there's no risk at all, that the difference is really null. And the other thing to remember is often there are follow-up studies. There was a follow-up study again by another individual, Rose, Korean War veterans, 40 years later. A lot of, looks like a lot of blue ribbon people here from National Cancer Institute, National Academy of Sciences, and so forth. And what did they find? This was essentially a study that was done 20 years after Robinette. And again, they followed 40 years of mortality in these veterans. Deaths from all diseases were still significantly below expectation. And for the 20,000 sailors with higher radar exposure potential, there was no evidence of increased brain cancer in the entire cohort, no significant excesses. So the bar chart doesn't accurately portray the Korean War Navy veteran health outcomes, so you have to be on the alert for issues like that. I could say a few things about long-term use of cells. Sometimes it's said, well, we just haven't used them long enough. And again, there have been a number of reviews on that. This is Albaum and colleagues in 2009, and they looked at epidemiological evidence. And they looked specifically at long-term use. Glioma, pooled analysis, looked at the large number, found an odds ratio of 1. That means no risk at all among persons who started to use a mobile phone 10 or more years before a diagnosis. Second cancer, meningioma, largest study so far, found odds ratio of 0.9, long-term use. acoustic neuroma. Pooled end of all studies gave a summary risk of 1.2 and 1.1 for every use. So these, again, are not statistically significant. No consistent evidence of increased risk. So rather than sort of accepting a statement that, oh, that must be true, that's not the case. I guess what I will end with is the Albon also did a follow-up study of brain cancer, and one of the interesting graphs he published, and I'll stop here, is he looked at time trends of brain cancer specifically in Sweden for 25 years after widespread introduction of mobile phones. And you notice here he has the age-adjusted rate. The blue lines are the older people, that's older than 60. The red dashed lines are 40 to 59-year-olds, and then the green lines are the youngest people. So brain cancer incidence increases with age, and that's why these lines are higher as you get older. Mobile phones were introduced here in Sweden in 1987, and so what Albon and colleagues did was they plotted both in men, upper chart is men, lower chart is women, they plotted in men and women the time rate of change in these three age populations, youngsters, middle-aged, and oldsters, and there's a lot of noise, a lot of bouncing around. That's kind of nature of signals that you get in epidemiology. But basically they concluded that these charts, these time changes, do not show any trend in increasing brain cancer rates. The same kind of study has been done in the United States, and also shows that there's no trend of increasing brain cancer rates from cell phones. So there's a plethora of literature out there, and you need to examine it kind of closely, and that's why it makes sense to rely on the agencies that have groups of experts that are specifically looking at these things from all sorts of angles to try to determine what the integrated picture is. And so perhaps I should just stop there and and go on to questions.
Thank you.
My name is Steve Patel. I'm one of the 5 commissioners. Only 4 of us are in attendance today, and so there's an audience of, just guess, like 60 or 70 folks who are listening in as well. Thanks so much for your presentation. I really appreciated it, and it helped me begin to resolve a lot of questions that have been raised in the last several months since I've been commissioner. I do want to hone in a little bit more, if that's okay, on the cell phone studies, because the thing that I have, I don't read the studies the way that you have. I just hear of them when people come in and speak at the podium giving public testimony, and I read a little bit on the internet, etc. What was persuasive to me in my limited knowledge was what people quote that these cell phone studies are showing that there's an increased brain cancer detected on the side of the head that people commonly use their cell phones on. Can you comment on that study and give us a little more information about it?
I think I have heard of that study, and my understanding is that, yes, there may have been a study that indicated that for a brief period of time, but that was really only one study out of many studies. And in fact, if you look at the summary papers, if you want, I could in fact track down that specific paper for you and send it on. That the increased incidence on the side that the phone was used turned out to be a flash in the pan. It did not hold up when you looked at the broader spectrum of data that was available for cell phones. And so you're right. In a way, that sounds kind of interesting and perhaps alarming if there is an increased incidence in the part of the head that could conceivably be getting more energy. Then that's something that deserves closer examination. But it did not hold up under closer examination.
I'm Dr. Valberg, John Brown, EWIP Commissioner. We are in a community that scrutinizes things such as this very heavily, as evidenced by the input we've had here. So a question regarding cell towers and things such as that. Our community doesn't differentiate on where they're located with respect to what they emit, that it's only on a land use. And so we've had recent decisions where they put the cell towers in very close proximity to schools and very close proximity to permanent residence, multifamily apartments, and things like that. And could you just go over again the level of RF that a cell tower, a regional cell tower would emit compared to a smart meter or a smart meter transmitter, or that? how how much more RF would I have from the cell tower within 100 feet of my home versus smart meter?
Well, yes, I'd be glad to say a few things. It's hard to make generalities because all of these things are really quite site-specific and cell tower specific, but there are a couple things that can be said, in a general way. As I said, for cell towers, the radios inside a cell tower are typically of the order of 200 or 300 watts. And of course, the actual amount of energy coming from a cell tower depends a little bit on its use and how many consumers are using it at a particular time. So the energy is quite a bit higher than a smart meter, which, as I say, is limited to about 1.5 watts. So it could be 200 times higher. Now, as with everything, as is the case with the smart meter, as is the case with the cell tower, everything falls off with distance. And so basically that 100 watts, you're not as close to the antenna, generally speaking, as you would be to the smart meter. So that those waves also drop off with distance. I guess in terms of cell phone tower siting, the other thing that's important to remember, and I don't know how you take this all into account in your decisions and so forth, there is a little bit of a counterintuitive aspect to cell tower siting in the sense that the more of them there are, the lower their energy. The initial cell towers had to reach long distances of the order of miles, so they had to have powerful transmitters, and there were many people who were getting a signal in excess of what they really needed. And strangely enough, as you increase the population of cell towers, each one can be weaker and weaker and weaker because it doesn't have to go as far. And it also has a benefit at the receiver end. My cell phone doesn't have to work hard to reach the nearest base station if the nearest base station is close. So in a kind of global sense, because of the nature of cellular technology, as the number of cell towers proliferates, everybody's RF exposure goes down. And so that's just another aspect to keep in mind. You were talking about putting a cell tower close to a particular facility. You have to remember, if you don't put the cell tower there, that facility, that location still has to be served by other towers. And so, radio waves will still get there, and they may actually be at higher levels than if you put a tower where most of these towers are essentially designed to shoot over the nearby locale. They're kind of focused like a little bit like lighthouses.
Thank you.
Commissioner, or Dr. Valberg, this is John Simpson, Commissioner Simpson. FDA and FCC regulations require all cell phones in the United States to have a specific absorption rate of less than 1.6 watts per kilogram. What is the SAR of a smart meter at 1 foot distance? And what's the SAR walking down a sidewalk in a residential neighborhood?
Well, the SAR of a cell phone is much higher. The transmitter in a cell phone typically has about 2 or 3 watts power. And so when you're holding a cell phone and you're holding it next to your head, again, the actual SAR you get depends on how far the nearest base station is and various things that are hard to generalize about. But what you need to think about is you're holding that cell phone within millimeters of your head, and you're holding a transmitter of 2 to 3 watts of energy within 2 or 3 millimeters, whereas you're comparing that to a smart meter that's about 1.5 watts transmitting, but that's very intermittently actually, but let's say it's on all the time, and you're, let's say, 3 feet away. Well, the amount of energy at 3 feet, the SAR is going to be very low. And I tell you, I can't give you an answer to your question numerically. I would have to calculate it. But just giving you that scaling that you've got a 2 to 3 watt transmitter very close to your head on a cell phone and a 1 watt transmitter at least 1 or 2 or 3 feet away. And as you saw from those charts, the energy there drops off rapidly. So I would suspect that the SAR, the actual absorbed energy, would be dropping off quite dramatically as well.
Thank you.
Dr. Valberg, this is Commissioner James Manning. How are you today, sir?
Oh, good, thank you.
Thank you for your presentation. I just have a small question. It's kind of a sideline, but I know I use a Bluetooth for my cell phone. use and stuff, and so that's always in my ear. Is there a significant difference between walking around with a Bluetooth in your ear and the transmission of a smart meter?
Oh, that's it. And I guess I probably can't answer that specifically. I would say that the Bluetooth is probably weaker than the smart meter, and I generally use, the principle I use is that it depends upon the distance that you have to transmit. And the Bluetooth earpieces are built to transmit from your ear to wherever you're keeping your cell phone. And so let's say you're keeping it in your pocket. So you're talking about a distance of, let's say 3 feet. So they're not going to over-design the transmitter and have the battery run down. So that would be low. The smart meter is going to be reaching a receptor that's farther away than 3 feet. So my rule of thumb in your question, which I apologize, I can't give you a numerical answer, but my rule of thumb would be that the Bluetooth is weaker than the smart meter.
Thank you. I was kind of just wondering about that since I use it all the time. That's good to know. Thank you, sir.
I have one other question, Dr. Valberg. So you mentioned a number of maybe call them characteristics of RF, the amplitude, the frequency, the power output, etc., and how they've been studied in great detail and proven not to, disrupt molecular functions. Are there other characteristics that scientists have discovered about radio frequency that might merit additional research that might interact with human tissue in ways that the first 4 or 5 that we studied to death don't?
Well, there's been a lot of thought about other possible aspects. I mean, you probably know that there's been some thought on modulation. I mean, is there a difference between AM and FM signals? Is there a difference between AM and FM and pulse signals? And so the way that the carrier wave is modulated might make a difference, you might argue. And all of those studies that have looked at that have basically concluded that the only thing that is really important is the amount of energy delivered, the frequency and the energy. The frequency kind of determines the amount that's absorbed by the body at different frequencies, and different frequencies are absorbed more efficiently than others. So, there have been thoughts about, well, maybe the direction of the propagation is important, maybe the direction of that relative to the Earth's magnetic field is important. So a variety of theories have been bandied about, but the bottom line is that so far none of those have panned out, and it seems to boil down to intensity of the RF and the frequency, and particularly the photon energy that have become the most important.
Thank you.
So I think we're going to transition at this point. Thank you so much, Dr. Valberg. You're going to stay on the phone and listen to the next presentation and be available for follow-up Q&A. So hopefully we don't lose you, but we'll check back in with you.